This video will continue discussing finding extrema of surfaces in 3-space. So in the process of that, we're going to have to solve systems. So I would like to do a small video of review of some systems because I know in algebra classes, they tend to skip over the nonlinear systems. So a couple notes. I'm going to do the first two here. These are the ones that are going to pop up often and are pretty straightforward. Remember, we want to take our partials and set them equal to 0. So the system for number 1 looks like this. It's 2x minus 4 equals 0, and 3y plus 9 equals 0. Well, I can solve that system just by solving for each variable. X is 2, y is negative 3. So my critical point, CP, is going to be 2, negative 3. Right? Same thing here on this system. If I get that the partial of x is 4 and the partial of y is 9, and I had to solve that system, that doesn't exist, right? 4 does not equal 0, 9 doesn't equal 0, so no CP here, no critical points. We'll write it here. No critical points. And then if neither one of those work, then you just have to find some way to solve the system. I know that's not helpful. This is me trying to help with point number 3. I'm going to do a bunch of examples of systems. All right, here we go. So here's the first one. I know the system that I'm going to create is by taking my partials and setting them equal to 0. So I got 3x squared minus 3y equals 0. And then I got negative 3x plus 3y squared equal to 0. All right, so we're working this out. We're trying to get that to work out for us. Do whatever you can to plug into the other in some way, or find some way to knock down powers, anything like that. Okay, so what I'm looking for is maybe to plug one into the other. I'm thinking maybe we can do this. Y is equal to x squared. I don't know if you guys can see that. If I divide it, I got minus, or if I take it over, I got negative 3 on the right. Divide by negative 3, then they're gone, and that's what I get left with. Okay, what I'm going to do here is I'm going to take x squared, or y rather than, and plug that into the other equation. So I'm going to get negative 3x plus 3 times x squared squared equals 0. So that gets me negative 3 plus 3x to the 4th equals 0. Now, you may be looking at like, I don't know how to do that one. One, I'm going to flip it around because it makes me feel better about it. But we don't have to do that. It just makes me feel good. Notice that there's a 3x in both terms. Leaves me with an x cubed minus 1, which is equal to 0. The zero product property tells me once I get down to a product like this that equals 0, each term, one of the terms must be 0. So either x is 0 or x is 1. So we are going to get 2 critical points now from that by plugging it into the equation well above. This tells me that if x is 0, y is 0. And then if x is 1, y is 1. That's plugging into this equation above. So my critical points are 0, 0, and 1, 1. So we're going to run this through the Hessian. I'm going to shrink this part up. All right, so there are my critical points. I need to come up with the Hessian, so I'm going to need fxx. I got x up there, so that is going to be 6x. I'm also going to need fyy, which is going to be 6y. And I'm going to need an fxy, so I'm going to use x up there. Fxy is negative 3. Now I plug this into my Hessian. So I got 6x times 6y minus negative 3 squared. So that's 36xy minus 9. Now I plug each point in. If I plug in 0, 0, I get negative 9, which is less than 0. This tells me that the point 0, 0 is a saddle point, like the one we discussed above there. All right, now I want to plug in, using that same thing, I'm going to plug in 1, 1. And we get 36 minus 9, which is equal to 27, which is greater than 0. Okay, so it's either a relative max or a relative min. And then now I have to plug it into XX, the 1, 1. And I get 6, so that's greater than 0. So both of those together tells me, okay, greater than 0 tells me it's a relative max or min. Greater than 0 tells me concavity is up, which tells me it's a relative minimum at the point 1, 1, f of 1, 1. And you can plug that in if you wanted that point. I think f was actually, we don't have f. So there we have it. We could probably figure out f. You guys could probably think of a way to do that. We're not there yet in our notes, but probably could think about it. So here we go. We have 0, 0 as a saddle point. And we also have that there's a relative minimum at 1, 1. So, we just had to solve the system here. We didn't have to do the Hessian, but we'll leave it. That was extra. That was bonus. So this is bonus. They didn't even ask for that. Okay, so let's look at another system. And I won't go all the way here. 2x minus 6 minus the square root of y. We're setting these equal to 0 to create a system. All right, plus 1, and that's equal to 0. All right, I see that square root of y, and that's what is I'm looking at. I'm like, oh, we should find some way to make that better for us. So I'm actually going to manipulate this equation. I got 1 equals x over 2 times the square root of y. That's just adding that term over. I'm going to multiply both sides by 2 squared to y, and that's going to be equal to x. So that means the square root of y is equal to 1/2 x. Now I'm going to go to the other equation, the top one. So I don't know what that arrow was. That and this together, and we got 2x minus 6 minus 1/2 x equals 0. Now notice there's only an x. I'm going to multiply everything by 2. So we got 4x minus 12 minus x equals 0. So we get 3x equals 12, which means x equals 4. If I have x equals 4, all I got to do is use the square root of y equals 1/2 x, plug in x and solve for y. I got the square root of y equals 2, so that means y is equal to 4. So do whatever you can to get rid of the weird part, and things typically work out for us. Worst comes to worst, you can use this system thing online, but really when it comes down to this isn't going to work in a linear solver. You would have to do something else. I'm sure those calculators exist, but I'm going to give you systems that you can handle. All right, I got a few more here. All right, just making them a little more complicated as we go on. So we're creating a system. So I'm going to set them all equal to 0. All right, that's equal to 0. Then I got 3x minus x squared minus 2xy equals 0. There we go. So there's our system. And we got to find one way to get it to work out for us. Let's notice that bottom equation, that there is an x in every single one of those. So x times 3 minus x minus 2y equals 0. We are going to work from this, and using this other idea, we have y here. Notice I can do that same thing. Kind of. Equals 0 looks a little different, but it's the same thing. So I'm going to use this, the one on the bottom, to create some scenarios. If x equals 0, that's what I'm going to start with first. And what I'm going to do is use the other equation to figure out how that's going to work out, what y is going to be. So if x equals 0, I'm going to replace that. I get 3 minus 2 times 0 minus y equals 0. So I got 3 minus y equals 0, which means y equals 3. So there's one critical point. We're not going to check any of these. We're just working on systems. So there's 0, 3. Now the other one is going to be 3 minus x minus 2y equal to 0. All right, and we're going to have to use this to work with the other thing. Okay, so I can solve for x here. If I add x to the other side, I got 3 minus 2y. I'm going to now plug that in. This was that second one. I'm going to plug this into the other function. So I got y times 3 minus 2. Now this is where I'm going to plug that in. Minus y. It's not pretty, but it works. I got y equals, or y times 3 minus 6 plus 4y minus y equals 0. Combine like terms. I got negative 3 plus 3y equals 0. This tells me y equals 0. And it also tells me negative 3 plus 3y equals 0. Which is, okay, if I add 3, I get 1. Okay, so these are going to give me two different points. If I plug that in, and I'm thinking right here is where I'm plugging it in. If I plug in 0 there, I get x is 3, y is 0. And then doing 1 there, 3 minus 2 times 1 is 2, 1. So I get 1, 1. So those are my critical points right there. So these systems are going to be a bit tricky, given the name tricky systems. But you can find a way. That zero product property that we used right here, right? We took this and set it equal to 0, and then we took this and set it equal to 0. That zero product property is going to get you out of a whole lot of things. Right? Let's take a look at one more. All right, so I set up this system. I got e to the x sine y equals 0. I also have e to the x cosine y equals 0. Now this one's going to be a bit tricky. What I want you to notice is that e to the x will never be 0 for any x. Never will, right? If it's negative, e to the negative just flips it over. It doesn't make a negative number. That will never be negative. So for this to be true, I need sine y to be equal to 0. And then I also need cosine y to equal 0. We don't care about the e to the x because it'll never be 0. So really our whole new system is right here. Any x will work. But if you can think back to trig, this never happens, right? We never have that the sine and cosine will be, like, there's no value that will give me 0 for both. Now, are there times that sine and cosine are the same value? Yeah, but they're never 0 at the same time. So there is no solution to this system. So sometimes looking at some functions that will never be 0 will unlock some patterns for you to use. So look for stuff like that. Mainly when I'm working a system, I'm doing anything I can to get rid of the weird part. Typically when I do that, things kind of fall apart like they did in these examples.